Hello friends. So today we are going to solve the questions from chapter Heat and Thermodynamics, and we are going to solve for the 2022, and total questions we are going to solve are 23, and all these questions are from the mains. And this is part 2 for the year 2022. So the first question, it states that sound travel in mixture of 2 moles of helium and n moles of hydrogen. If RMS speed of gas molecules in the mixture is square root 2 times the speed of sound, then the value of n will be. So here we are supposed to find out value of n, that is the number of moles of our hydrogen. And it is talking about RMS speed. So we are going to start with the formula for our RMS speed. And we know that our RMS speed, which is given as VRMS, is equal to 3RT divided by m and its square root. And we are given the question that the RMS speed is square root 2 times the speed of the sound. So let's assume that the speed of the sound is V. So you can say for speed of sound is V, therefore we can write that our VRMS is equal to square root 2 times V. And we can also find out this formula for V in terms of our RT as well as M. Okay. And so let's find out the speed of sound. Speed of sound for ideal gas mixture, which we denoted as V, and this V will be equal to square root of gamma P upon our rho. So this is our P. Here P is the gamma is the adiabatic index, and P is the pressure, and rho is our density. And this density can be also written as our mass oblique volume. Okay. And from ideal gas law, we also know that our PV is equal to our nRT. Okay. And Therefore, we can write that our density will be equal to our, in place of this m, we can write our number of moles divided by molar mass and our volume. Okay. And we can substitute our volume. So we get this as our Nm, and our volume is nRT upon P. And n cancel with n, so we get our density will be equal to P times m divided by our RT. And we have to remember this capital M is our average molar mass. Okay. Therefore, we substitute in the equation, we get our V is equal to, and we have this as gamma, and our P, and our density is our P times Pm divided by RT and its square root. Here P cancels out with P, which gives us that it will be equal to gamma RT divided by m square root. So this is the equation for our velocity of the sound. So we come back to our this equation. Let us call this equation number 1. So on the left side we are going to substitute the RMS equation, and the right side we are going to substitute the velocity of sound equation which we just found out. So we can say from equation 1, we have our 3RT upon m square root is equal to square root 2, and this is gamma RT m and its square root. So if we square completely, this square root cancel out throughout. Accordingly, our this m and RT also goes away. So we are left with our 3 is equal to 2 times gamma. Therefore, from here we get gamma is equal to 3 by 2, or we can say that is equal to 1.5. Now it is said that is a mixture 2 moles of helium and n moles of hydrogen. So we are given that we have a mixture, and that mixture is of helium. Helium is our monatomic, and for that our adiabatic index for monatomic we know is our 5 by 3, and its molar mass is our 4 gram per mole. And next is our, okay, and we are given that it is of 2 moles. And next composition is of our hydrogen, and hydrogen is our diatomic, and this gamma for our hydrogen will be equal to 7.5, and its molar mass will be equal to 2 gram per mole. And this particular question, it states that there are n moles. Therefore, we can find out the adiabatic ratio for the mixture. So we can say for our gamma for a mixture, we can use the general formula, and that general formula is our summation n of I, constant pressure of I, divided by n of I, constant volume times I. I will be any number of mixture. Here it is 2 mixtures, so I value of I is going to be from 1 to 2. And we also know that our Cp is equal to our C of V plus R. And this C of V of I will be also equal to F of I R divided by 2, where F of I is our degree of freedom. Okay. So according to the gases, we can say first of all is our helium. Helium, we can say our F of our He, degree of freedom, is our 3. Therefore, our C of V of our helium will be equal to 3R upon 2, and our C of P of our helium will be equal to 3R of 2 plus R, which will be giving us 5R by 2. Similarly, we can write for hydrogen. Hydrogen, its degree of freedom is our 5, and with no, we can say, no vibrational modes, and its C of V for our hydrogen will be now 5R by 2, and our C of P of our hydrogen will be equal to 5R by 2 plus R. That will be giving us 7R by 2. And number of moles, total number of moles, usually number of moles we represent by small n, but in this case we are going to represent, in this particular question we are going to represent it with capital N, and this will be equal to 2 plus small n, because this small n has been already used. Therefore, we can say that our C of V mix will be equal to 2 times our 3R by 2 plus n times 5R by 2 divided by total number of moles, and this can be written as, this will be coming as 6, and so it will be 6R plus R we can take common, so this will be 6 plus 5n, and this comes as 2 multiplied by 2 plus n. And similarly, we can find out our C of P of mix will be equal to this will be our, for mixture we found out, so this will be equal to 2 multiplied by 5R by 2 plus n multiplied by 7R by 2, and this comes as 2 plus n. And here also R we can take as common, so this will be coming as 10 plus 7n divided by 2 plus multiplied by 2 plus n. Now we can take the ratio. So we can say that our gamma of our mix, which we also found out is our 3 by 2, and we can divide them. So if we divide these two equations, we know that this denominator is going to cancel out, and that will be coming as our r, and r also goes away. So this is C of P of mix divided by C of V of mix. That will be 10 plus 7n and 6 plus 5n. So now it is quite easy to solve. We just cross multiply. We get this as 18 plus 15n is equal to 20 plus 14n, and it will be coming as n is equal to, this will be our 20, 18, 2. So value of n is our 2. So option B is correct. B is correct. Next question. It states that a gas has n degrees of freedom. The ratio of specific heat of the gas at constant volume to the specific heat of the gas at constant pressure will be. Okay. So here we have to find out the ratio of C of V to C of P. And so it is said that it has n degree of freedom. Therefore, we can write that our C of V will be equal to our n r divided by 2, and our C of P, which is our C of V plus r, and that will be equal to our n r 2 plus r. So r we can take as common, so this will be coming as n plus 2 divided by 2. And we are required to find out the ratio. So we can say ratio is of our C of P to C of P. And we can say this will be nr upon 2, and this will be r n plus 2 upon 2. And here this r2 cancels out. So we get this will be equal to our n upon n plus 2. So n upon n plus 2, option A is correct. Next question. It states that same gas is filled in two vessels of same volume at the same temperature. If the ratio of the number of molecules is 1:4, then we have to check which of these options is correct. First, A option states that the RMS velocity of gas molecule in two vessels will be same. Okay. And we know that our VRMS is given as 3RT and divided by M. Okay. And here this RMS is, you can say, dependent upon R is our constant, so it is only dependent upon our T and M. But in the question it is given that it is a same gas, so the M will be same for both, and it is having same temperature, so therefore temperature will be also same. So therefore we can say that our RMS velocity for both gases will be same. So option A is correct. Next says that the ratio of pressure in this vessel will be equal to 1:4. So for that we can use our ideal gas law. which gives us that PV is equal to, and nRT. Okay, here capital N is number of molecules because it is given as this number of molecules. Okay, so let me write it here. So this is a capital N is our number of molecules. And we are given that they are having same volume and same temperature. Therefore, from here we can write our P will be proportional to our N. Or we have two guesses, so we can say our P1 upon P2 is equal to N1 upon N2. And the ratio is given as 1:4. So this comes as 1/4. So ratio is our 1:4. So option B is also correct. And ratio of pressure, obviously, so this is incorrect because the ratio is 1:4. And D states the RMS velocity to vessel will be in the ratio. Okay, so we just concluded that the RMS will be same, so option D is also incorrect. So only A and B is correct, so option C is correct. Next question. It states that which of these statements are correct about degrees of freedom? Choose the correct answer from the options given below. So it states that first option is a molecule with n degrees of freedom has n raised to power 2, or we can say n square different ways of storing energy. And so if the degree of freedom is n, then the different way of storing the energy is also n. Okay, so it's not n square, so option A is incorrect. And B states that each degree of freedom is associated with 1/2 RT average energy per mole. Okay. And this is based on our equipartition theorem, which states that the degree of freedom is equal to 1/2. Sometimes it is written as KT and sometimes it is also written as RT. Okay. So this option is correct. Option C, a monatomic gas molecule has one rotational degree of freedom, whereas a diatomic has two rotational degree of freedom. Okay. So you can say that our monatomic gas molecule, suppose we take as helium, it is going to have 3 translational degree of freedom and no rotational. Okay. Or we can say that so there will be no rotational degree of freedom, and in case, so obviously this option is incorrect. In case of diatomic also, we can say that this 2 rotational degree option is correct, but the first part is incorrect. And D states that CH4 has a total of 6 degrees of freedom. Okay. And so our CH4 is basically a polyatomic, and that's a non-linear as well as it is tetrahedral. Okay. So it is going to have our 3 translational and 3 rotational. Okay. So ideally we sometimes also consider vibrational also, but in this particular case ideally they should have mentioned, because at the low temperature we consider that there is no vibrational movement, a vibrational degree of freedom. Okay. So there will be only 3 plus 3, 3 rotational and 3 translational. So option D is also correct. So from here we get B and D are correct. So option B is correct. Next question. It states that a vessel contains 14 gram of nitrogen gas at a temperature of 27 degrees centigrade. The amount of heat to be transferred to the gap to double the RMS speed of its molecule will be, take R as 8.32. So we want that the RMS speed should double, so we need to find out the amount of heat that is required. And so we are given 14 gram of nitrogen gas. So first of all, let's find out the number of moles of this for nitrogen gas. So we can say the number of moles, which is ever n, and that will be equal to the given mass and its molar mass, that is about 28. So which gives us 1 by 2, or we can say this is equal to 0.5. And the general formula for our RMS speed, so we know that our VRMS is equal to 3 RT upon capital M and its square root. And so this formula we can divide into two different temperatures. First is at a given temperature, which is 27 degree. Let us assume that is our T1. And second, because we are going to supply the heat, its temperature is bound to increase. Okay. Let's suppose that temperature is our T2. Therefore, we can say that our VRMS 1 is equal to 3 RT T1 upon M and its square root, and we can say our VRMS 2 is equal to 3 RT T2 M and its square root. And we want that the RMS speed should double. Therefore, we can write that our VRMS 2 should be equal to twice of our VRMS 1. So we substitute the formulas. So we get this as our 3R T2 upon M and square root is equal to 2 times, and this comes as 3R T1 upon M, and we square both sides. So squaring both sides is going to give us 3R T2 upon M is equal to 4 times 3R T1 upon M, and here this 3RM cancel out. So from here we get our T2 temperature is equal to 4 times T1, and T1 is our initial temperature, which is given at 27 degrees centigrade. So we know that our T1 is our 300 Kelvin. Therefore, we can say our T2 will be equal to 1200 Kelvin. And we are given nitrogen gas, which is diatomic. So we have our nitrogen gas, and that is our diatomic, and its degree of freedom will be equal to 5. 3 rotational and 3 translational and 2 rotational. Therefore, its C of V can be written as 5R upon 2. And we need to find out the heat. So now we can just find out our Q. We can say the heat at constant volume which is a Q is equal to N C of V multiplied by delta T. Okay. And N is our 1 by 2, so we simply substitute them. We get our Q is equal to 1 by 2, C of V is our 5 by 2, and R is our 8.32 multiplied by the temperature difference, and temperature is our 1200 minus 300. And so from here we get that the value of Q will be approximately equal to 9360 joules. So we have 9360, option C is correct. Next question. It states that at a certain temperature, the degrees of freedom per molecule for gases is 8. The gas performs 150 joule of work when it expands under constant pressure. The amount of heat absorbed by the gas will be. So we have to find out the gas and it heat absorbed, and it states that it is under constant pressure. Okay. So we can say, we can use our constant pressure. Work done is our, so we can say work at constant pressure W is equal to P times delta V, and that work done is given as our 150 joules. And in this case, number of moles are not given, but for the sake of convenience, let us say that value of N is equal to 1. And we can say that our C of V is, because degree of freedom is given to us, so we can say this will be F upon 2 times R. F is our 8, so this comes as 8 upon 2 times R, which giving us 4 times R. And from here we can find out our C of P, which will be equal to C of V plus R, and this gives us 5R. And we can find out our change in internal energy, and or let's use our straightforward, we can say from first law of thermodynamics, from first law we have that our heat is equal to delta U plus work done, and our delta U, or let's use first of all the work done. So work done at constant pressure is our NR times delta T, and so from here we can find our delta T is equal to W upon NR. So this comes at W is our 150, and N we have assumed that is 1, and this comes at 8.31. So we get our this delta T change in temperature is close to 18.05 Kelvin. Now we can find out our delta of U, change in internal energy, will be equal to N C of V multiplied by delta T, and this comes as a 1. C of V is our 4 times R, that is our 8.31, and delta T is 18.05. So delta of U will be close to is equal to 600.3 joules. Now we can find out our Q. So we get that the heat Q delta is our 603 plus work done is over 150. So this comes approximately as our 750 joules. So it will be equal to 750. Next question. It states that the pressure P1 and density D1 of diatomic gas gamma is 7/5 changes suddenly to P2, where P2 is greater than P1, and D2 respectively during an adiabatic process. The temperature of the gas increases and becomes dash times the temperature of initial. Okay, and the ratio of their density is given to us. So the process is adiabatic, so we can use directly the formula. We have our adiabatic process, and for adiabatic process we know that T multiplied by V gamma minus 1 is equal to constant, and it is talking about the density, and density is given as D, so we know that our density is equal to mass oblique volume, and so we can say that our volume is equal to mass oblique density. And so we have same gas, so this mass will be constant. Therefore we can say that our V2 upon V1 is equal to our D1 upon D2, and D1 upon D2 is our 1 upon 32, and we can extend our this adiabatic process equation as our T1 V1 gamma minus 1 is equal to T2 V2 gamma minus 1, and we can say that our T2 upon T1 is equal to V1 upon V2 whole raised to power gamma minus 1, and this is equal to 1 by 32, so this comes as our 32 gamma minus 1, and gamma is given to us as 7/5, so this becomes 2 by 5, so this will equal to 32 and it will be equal to 2 by 5, so this will be coming as 4. So we get that our T2 upon T1 is equal to 4, or we can say our T2 is equal to 4 times T1. So final temperature is 4 times the initial temperature. Next question. It states that 1 mole of monatomic gas is mixed with 3 moles of diatomic gas. The molecular specificity of mixture at constant volume is alpha square upon 4. Then the value of alpha will be, assuming that diatomic gas has no vibrational mode. Okay. So we are given that we have monatomic gas and its degree of freedom will be equal to 3. So we can find out that it is C of V, mono we find out, and it is mixed with, okay. So basically we are going to find out C of V for the mixture, and from there we can take, because specific heat at constant volume is given as alpha square upon 4. So we can say that for our monatomic, we know that our degree of freedom is equal to 3. Therefore we can say our C of V of mono is equal to 3R by 2. And for diatomic, there is no vibrational mode. Therefore we can say we have our diatomic and its degree of freedom, that is F, will be equal to 5. So we can say our C of V of our dia is equal to 5R upon 2. And number of moles for our mono is given as 1, and number of moles for our dia is given as 3. So we can say that our C of our mix will be equal to number of moles of mono multiplied by C of mono plus number of moles of dia multiplied by C of dia, and the denominator will be total moles, mono plus dia. And we substitute the value. This comes as our 1 into 3R by 2 plus 3 multiplied by 5R by 2. This complies 1 plus 3. And this will be coming as 15 plus 18, and 18 by 2 giving us 9. 9 by 6 will be giving us, 9 by 4, not 9 by 6. So we get our C of mix will be equal to 9R by 4. But we are given that the C of mix is equal to alpha square by 4 and divided by R. Here this R cancel out, 4 and 4 goes away. Therefore we get from here that value of alpha is equal to 3. So value of alpha is 3. Next question. It states that the root mean square speed of smoke particles of mass 5 into 10 to the minus 17 kg in their Brownian motion in air at normal temperature pressure is approximately equal to. Okay. So we have to find out basically the RMS speed at normal temperature pressure. So RMS is dependent upon temperature only. So normal temperature is 273 Kelvin. So we can say that our VRMS is equal to 3 kT and m square root, and normal, so we simply substitute the values. This will be giving us 3 K is our 1.38 10 to the minus 23. Normal temperature is our 273 Kelvin, and mass is given to us as 5 into 10 to the minus 17 and its square root. So we get the velocity will be equal to 15.03 meter per second. So option C is correct. Here the technical term Brownian motion is used, but we need not to worry. It just signifies the or denotes the how the particles are moving. Okay. So that it was discovered by, I think, scientist whose surname was something Brown. So that's why its motion is called as a Brownian. Okay. We can easily see it when there is some kind of light in a dusty room. Okay. So we see the particles are moving, and that particular motion is called as a Brownian motion, and that is governed by another specific equation, but that's not required. Next question, it states that a unit scale is to be prepared whose length does not change with temperature, remains 20 centimeter, using a bimetallic strip made of brass and iron, each of different length. The length of both components would change in such a way that difference between their length remains constant. if the length of the brass is 40 centimeter, the length of the iron will be. So linear coefficient of iron and of our brass is given to us. So here we have to keep in mind that if, because it is said that okay, it's a bimetallic strip and the length of the brass is given to us as a 40 and the length of the scale is given to us at 20 centimeter. Okay. So we have to remember that the effective length is always 20 centimeter and its length with respect to the, or we can say the difference in lengths of brass and iron remains constant with temperature, that is given in the question. Okay. So we know that the length change the general formula is our delta L is equal to original length, the linear coefficient expansion, linear coefficient and multiply by delta T. And here we are having two different components. One is brass, other one is our brass and iron. Okay, so we can say that our for brass we can write this delta L for our brass, and for our iron we can write our delta of our iron, but it is given that the difference between the length is remains constant. So it means these two length will be same. Okay, there is a constant difference. It means the amount with which the brass is going to change its length, the same amount will be in the iron also. So we can just write it as in terms of this given formula. So here on the left side we get length of a brass, coefficient for our brass, and we have a delta T is equal to, and on the right side we have length of our iron, coefficient of our iron, and multiply by delta T. And this delta T cancels out. So from here we need to find out the length of iron. So we can say our length of our iron will be equal to length of brass, coefficient of our brass divided by coefficient of our iron. So length of our brass is given to us as 40 and its coefficient is given as 1.8 into 10 to the power minus 5, and for iron it is given as 1.2 into 10 to the power minus 5. So this 10 and 10 goes away and this will be our 40, and this goes by 2 and this goes by 3 and 2 goes by 20. So we get this will be equal to 60 centimeters. Okay. So it will be equal to 60 centimeters. Okay. We have to remember that it is basically a bimetallic strip. Okay. So it means, because if we, okay, need not to go into that part, because if it is connected one after another, then it will be, because total length is always 20 centimeter. Okay, next question. states that a block of ice of mass 120 gram at temperature 0 degree centigrade is put in 300 gram of water at 25 degree centigrade. The x gram of ice melts as the temperature of the water reaches 0 degree centigrade. The value of x is specific heat of water and latent heat of ice is given to us. So in this case, the ice is going to melt by taking the heat from the water. Okay? So there will be heat lost by the water, and that heat will be used by the ice to melt. So we can use the conservation of energy, heat energy rather. So first of all, let's find out the heat lost by the water. Heat lost by water, Q is equal to mass of water and specific heat of water and our delta T. So we get, let us call this as QW, and we get this as our heat lost by water is equal to mass of water is given as 300 gram. So this comes as 0.3 times, it is given as specific heat 4200, and the delta T is equal to 25 minus 0, which comes as 31500 joules. And heat gained by the ice, or we can say heat to melt ice, let us call this as Q ice, will be equal to its mass of the ice that is melted, m of I, and its latent heat. So that is our x times 3.5 into 10 to the power 5. Now the heat gain will be heat lost. Therefore, we can say that Q of W is equal to Q of ice, which gives us 31500 is equal to x times 3.5 into 10 to the power 5. Therefore, we get that our x will be equal to 90 grams. So we get the value of x is 90. Next question. It states that an ice cube of dimension 60 by 50 by 20 is placed in an insulation box of wall thickness 1 centimeter. The box, keeping the ice cube at 0 degree temperature, is brought to a room temperature 40 degree centigrade. The rate of melting of ice is approximately equal to. So we have to find out the rate of melting of ice. And so for that, first of all, we have to find out the heat transfer rate. Okay, from that we can find out the rate of melting of the ice. Okay. And we know that our heat transfer rate, which is our dq by dt, is equal to k multiplied by a times delta t upon d. Okay. And a here is our surface area. So we can say our a is equal to, in this case will be surface area of cube. Surface area of cube. and that is equal to 2 into length breadth plus breadth height and length height. So this comes as 2 into, we have this as 0.6 times 0.5 plus 0.6 times 0.2 plus 0.5 times 0.2. So we get this surface area A is equal to 1.04 meter square, and D is our thickness, which is given as 1 centimeter. Therefore we can find out that our dq by dt will be equal to, K is given to us as 0.05, that is our thermal conductivity, and here 1.04, and we have the temperature is 40 degree and difference will be 40 minus 0 divided by D is thickness, which is about 0.01. So we get this dq by dt will be equal to 208. Now we can find out the rate of melting. Rate of melting, it means dm upon dt. Basically rate of melting is decrease in the mass, rate of decrease of the mass, and that will be equal to our in this case we can use our Q is equal to ml. So if you differentiate both sides, we get this as our dq by dt divided by L. Okay. Because we know that our Q is equal to m times L. Okay, so from here we can just easily divide this, find out the rate, and this comes as our 208, and it is given as 3.4 into 10 to the power 5. Therefore we get the rate of melting will be equal to approximately 61 into 10 to the power minus 5 kg per second. So option B is correct. Next question. If K1 and K2 are the thermal conductivities, L1 and L2 are the lengths, A1 A2 are the cross-sectional areas of the steel and copper rods respectively, such that K1 upon K2 is 9, A2 upon A1 is 2, L2 upon L1 is 2. Then for the arrangement shown in the figure, the value of temperature T of the steel copper junction in steady state will be. So we are given the figure. On the left side there is a furnace at a temperature of 450, and on the right side, extreme right, is our ice box at 0 degree centigrade, and in between there is a steel and copper of different diameter, or we can say areas are there, and their junction temperature is T, which we are supposed to find out. So in this case, this is directly based on the formula. So we can say that our 450 minus T will be equal to, this will be our rate of the heat dissipation, and multiply by our, this will be our for first portion. Okay, so this will be over the first part, okay, and that will be equal to over L1 upon K1, and this is our A1. Then same we can write for the second part. This is our T minus 0. So we get this as T minus 0 will be equal to because it's state as steady state, so this will be our dq by dt multiplied by our L2 upon K2 and our A2. So first equation is for our this part, and first equation is for our this part for the furnace and steel, and second equation is for our copper and ice box. Now simply we take their ratio, we get 450 minus T upon T is equal to this dq by dt is going to cancel out, and we will get this as our L1 K1 A1 multiplied by L2 K2 A2, and ratios are given to us. We are given L2 by L1, so this will be our 1 by 2 multiplied by K1 and K2. One second. I think. Okay, let me write it in the form of the given ratio. So we are given that we have K1 upon K2. So we can write this as K1 upon K2 multiplied by, we have our L2 upon L1. So this is our L2 upon L1, and we have our A2 upon A1. So this is our A2 upon A1. Okay, so let's substitute the values. So we have our A2 upon A1 is our 2, K1 upon K2 is our 9, and L2 upon L1 is also about 2. So here this 2 and 2 cancels out, and this ratio L1 K1 and L2, yeah, this is correct. So this comes as 1 upon 9. Let me check whether I've written this, because it looks a little bit confusing. K2 by K1 is 9. This is K2 by K1. So rest is okay. So this is our K2 by K1, and this will be coming as 9. So this ratio will be 9. Now it's correct. Otherwise it was okay. So we get this as our 450 minus T is equal to 90. So from here we get our T is equal to 45. So we have T is equal to 45 degrees centigrade. So option C is correct. Correct. Next question. it states that read the following statements, choose the correct answer from the options given below. So first option states that when a small temperature difference between liquid and its surrounding is doubled, the rate of loss of heat of the liquid becomes twice. So we know that our heat loss rate is directly proportional to change in temperature. So you can say our heat loss rate is directly proportional to change in temperature. So if it becomes twice, so option number A is correct. Second states that bodies P and Q have equal surface area maintained at a temperature of 10 and 20. The thermal radiation emitted by in a given time by P and Q are in the ratio of 1:1.15. So we can use our Stefan-Boltzmann law, and we have our Stefan-Boltzmann law, and it is given that surface area is same, therefore P will be proportional to 4th root of power. Okay. And therefore we can say that our P1 upon P2 is equal to T1 upon T2 and its 4th power, and the temperature is our 10 degrees centigrade. So then will be our 283 okay, so T1 will be equal to our 283 and 1 second, P and Q surface area, so we have 283 and 293 whole raised to power 4. Hmm. 10 and 20. P body is at 10 degrees centigrade. So we have P1 okay. One second. So we have 283 and something is wrong. Let me check the options whether it is question is correct or not. V equal surface area. Okay, sorry, I calculated it wrong. This is correct. I divided the entire terms. We have to find out the ratio. Okay. So we get this as our, therefore we can write this will be equal to 1 upon 293 divided by 283 and 4. So this comes as 1 upon, this will be about 1.03 whole raised to power 4, and this comes as 1.1 decimal 1.15. Okay, sorry, I just divided it completely. So option B is also correct. And we come to our next part. Carnot engine working, between this efficiency is 75%. Okay, so we can calculate the efficiency. So we can say the Carnot efficiency is equal to our 1 minus temperature of C and temperature of our cold and hot. So this is 1 minus 100 Kelvin of 400 Kelvin. So this comes as 100 upon 400, which will be giving us 75%. So C is also correct. And D, from the option we can clearly see that option A is the correct one, but still we can go at D. When small temperature difference between a liquid and surrounding is quadrupled, the heat loss is, okay, so this is entirely opposite of our, the D option is incorrect, because the heat loss is also will be 4 times, not twice. Okay, so we have option A is correct. Next question. It states that two metallic wires of identical dimensions are connected in series if rho 1 gamma if we have this as our rho 1 and rho 2, gamma 1, gamma 1, sigma 1. Sigma 1 and sigma 2 are the conductivities of these wires respectively. The effective conductivity of the combination is. So we have two wires, and so let us suppose this is our first wire of equal length. So we have this as L is its length, and conductivity, and we have second wire whose length is also L and conductivity is our 2. And so when they are combined, we can represent them by a single whose length will be about 2L, and its conductivity is, let us call this as our equivalent. So we know that our resistance and area of cross section will be same for both. So we know our resistance, which is given as L sigma A, and for identical dimension we can say our resistance is inversely proportional to our sigma. And if this is our R1 and R2 and this is our R effective, so when they are connected in series, so we can say our R effective will be equal to R1 plus R2, or we can say this will be equal to our L upon A plus L upon A, and we can write L upon A, we can take as common, so this comes as 1 upon sigma 1 plus sigma 2, and our effective will be equal to, length is our 2L and this is sigma effective times A is equal to L upon A, and this comes as sigma 1 plus sigma 2 and sigma 1 multiplied by sigma 2, and this length area cancels out, so we get from here our effective will be equal to twice sigma 1 sigma 2 divided by sigma 1 plus sigma 2. So we have option B is correct. Next question. We are given that nearly 10% of the power of a 110 watt light bulb is converted to visible radiation. The change in the average intensity of visible radiation at a distance of 1 meter from the bulb to a distance of 5 meter is A times 10 to the power minus 2. The value of A is. So first of all, we have to find out what will be the visible radiation, which is 10% of our 110. So you can say that visible power let us call this as a P is equal to 0.1 times 10, which gives us 11 watts. And we know that intensity at a distance intensity I is equal to our power divided by 4 pi r square. Here r is the distance, and we are giving two values of r. First of all, of r is about 1 meter, so let us call this as I1, which will be equal to p is of 11 and 4 pi, and this is 1 square, and this comes approximately at 0.875. And second is our r is our 5, so we get our I2 is equal to 11 upon 4 pi, and this comes as 5 whole square. And let me keep as it is, we can just divide them. So we have to find out the change. Okay, we need to find out the change. So let us, I thought it is only ratio. So this we have was 0.875, and this we get as 0.035. Therefore we can see our change, that is our delta of I is equal to I1 minus I2, which is 0.875 minus 0.035. So we get our delta of I will be equal to 0.84, or we can write this as 84 into 10 to the power minus 2, and we are given that this is equal to A times 10 to the power minus 2, which gives us that our value of A is equal to 84. So value of A is our 84. Next question. It states that a certain amount of gas of volume V at 27 degrees centigrade, temperature and pressure 2 into 10 to the power 7 expands isothermally until its volume gets doubled. Later, it expands adiabatically until its volume gets redoubled. The final pressure of the gas will be. So here we are having two processes. First is isothermal expansion, the volume is doubled, and second is our adiabatic, and in this case also the volume is once again doubled. So let us consider first of all our isothermal expansion. And for isothermal expansion, we know that our P1 V1 is equal to P2 V2, and if our initial volume is our V, so our final volume as our V2 becomes 2 times V. Okay. Therefore we can write that our P2 will be equal to P1 V1 upon V2, and this initial volume is our V1. So we get this our P1, we can substitute the value. P1 is given to us as 2 into 10 to the power 7 times V1, and V2 is our twice of V1. So V1 and V1 cancels out, 2 and 2 goes away, so we get the pressure is equal to 10 to the power 7 pascals. And second process is our adiabatic. So you can see we are having our adiabatic process, and which we know is our PV raised to power gamma is equal to constant. Therefore, we can write this as our P2 V2 raised to power gamma is equal to P3 V3 raised to power gamma. And here it is given that our V3 is double of our V2, or we can say 4 times of our V1. Gamma is given as, okay, it has to be gamma. Gamma is our 1.5. So from here we can write that our P3 will be equal to P2, and this comes as our V2 upon V3 whole raised to power gamma. P2 we found out is a 10 to the power 7, and we have our V2, that is our V2 is our twice of V1, and our V3 is 4 of V1 whole raised to power 1.5, which is basically 3 by 2. 3 by 2. And this V1 this goes by 2, and this comes as our 10 raised to power 7, and we have this as our 2 raised to power 3 by 2. And so we get our final pressure P3 will be approximately equal to 3.5 into 10 raised to power 6 pascals. So we have 3.5, option A is correct. Next question. It states that let nu1 is the efficiency of the engine at T1 for 47 and T2 147, while nu2 is the efficiency at T1 947 and T2 47, then the ratio of nu1 and nu2 is. So basically this is Carnot efficiency. So we can use the formula for our Carnot efficiency directly. We know that our Carnot efficiency, that is nu is equal to 1 minus cold temperature and our hot temperature. So we can write this formula into two parts. First is our nu1, and that is equal to 1 minus degree centigrade, so 420 divided by 720, and this we get will be equal to our 0.41. Similarly, our nu2 will be equal to 1 minus, and we have this as cold and hot 320, and 947, that will be 1220, approximately be equal to 0.73. Ratio is our nu1 upon nu2, 0.41 and 0.73. So this comes approximately equal to 0.56. Option B is correct. Next question. It states that 7 mole of certain monatomic ideal gas undergoes a temperature increase of 40 Kelvin at constant pressure. The increase in internal energy of the gas in this process is. So basically we would find out the increase in internal energy, and we have 7 mole of gas, okay, and that is monatomic. So we know that for our monatomic gas, degree of freedom is over 3, therefore we can say our C of V will be equal to 3R upon 2. So we substitute value of R, we get this as our 3 by 2 times 8.3, which gives us 12.45. Now we can find out our delta of U is equal to N C of V delta T. Number of moles are 7, C of V is 12.45, and delta T is our increase 40 Kelvin. So we get this will be equal to 3486 joules. So option B is correct. Next question. It states that a monatomic gas at pressure P and volume V is suddenly compressed to 1/8 of its original volume. The final pressure at constant entropy is. So constant entropy means it is adiabatic process. So we have constant entropy, which is our adiabatic process, and for adiabatic process we know that our PV raised to power gamma is equal to constant. Therefore we can write our P1 V1 gamma is equal to P2 V2 gamma, and we are given that the volume is 1/8 of original volume. Therefore we can say that our P2 will be equal to P1, and this comes as V1 upon V2 whole raised power gamma, and we have our, okay, we substitute, we need to find out in terms of P. So initial pressure is P1 is given as our P times this is our V1, and V2 is our V1 by 8, and it will be whole raised power 5 by 3. V1 cancels out, so we get this is our P and 8 raised power 5 by 3. So this will be cube root of 8, which will be 2, and 2 raised power 5 will be our 32. So we get our P2 will be equal to 32 times P. So option C is correct. Next question. Okay, this is same question. So it states that In first case, Carnot engine operates between 300 Kelvin and 100 Kelvin. In second case, as shown in figure, the combination of two engines is used. The efficiency of this combination in the second case will be. Okay. So we given it operates between 300 and 200 and 200 and 100. Okay. So we have to find out the efficiency. So we know that our Carnot efficiency which is nu is equal to 1 minus cold temperature and hot temperature. So for our first case, is our, let us call this our new one, is equal to 1 minus, it operates between 300 and 100. So this comes as a 100 upon 300, which will be giving us as 2 by 3. And we are having a second case. And second case, we need to find out our net efficiency will be equal to nu1 plus nu2 minus nu1 nu2. And so okay, let me write first case this as our prime, so it is differentiable from this. So in this particular case, our nu1 will be equal to 1 minus 200 upon 300, which gives us 1 by 3, and nu2 is equal to 1 minus 100 upon 200, which gives us 1 by 2. Okay, so in this case we have to remember that this particular figure, this entire figure is the representation of the second case only. Okay, first case is given in the question independently, that is our 300 and 100. Okay, so this is entire combination is our second case only. So we can say our net efficiency will be equal to 1 by 3 plus 1 by 2 minus 1 by 3 times 1 by 2, which will be equal to our 1 by 6 minus 5 by 6 minus 1 by 6. It will be 5 by 6 minus 1 by 6, which will be equal to 4 by 6, giving us 2 by 3. And this is nothing but our this n1 prime. So we have option A is correct. Next question. It states that a Carnot engine has an efficiency of 50%. If the temperature of the sink is reduced by 40 degree, the efficiency increases by 30%. The temperature of the source will be. Okay, so in this case, we have two cases, temperature reduced and efficiency is increased. Okay, so let us start with the basic formulation, which gives us that our initial efficiency initial efficiency, that's our nu is our 0.5, which will be equal to 1 minus temperature of cold and temperature of hot. And from here we can say that our temperature of cold to temperature of hot will be equal to 1 minus 0.5, giving us 0.5, or we can say our temperature of hot will be equal to twice temperature of cold. And it says that temperature of sink is reduced by 40 degree centigrade. Therefore we can say that new sink temperature will be equal to, let us call this as Tc prime, is equal to original temperature minus 40, and new efficiency increases by 30%. So we can say our new efficiency we have a new efficiency, let us call this as new prime, and it increases by 30%. So we come this as 0.5 and 30% of our 0.5. This will be coming as 0.65. So we can write the formula that our new efficiency will be equal to 1 minus new cold temperature, and our hot temperature is our same. So we get this 1 minus Tc upon 40 divided by twice Tc, and we can take twice Tc as LCM. So this comes as about twice Tc minus Tc plus 40, which gives us twice Tc, and this comes as our Tc plus 40, and this will be equal to 0.65. So from here we get our Tc plus 40 is equal to twice of, it will be equal to 1.3 times Tc, or we can say our Tc will be equal to 0.3, that is 40 divided by 0.3, 0.3, which will be approximately equal to 133.33 Kelvin. We have to find out the temperature of the source. So we get our T of H is equal to twice Tc, which comes twice of 133.33 is equal to 266.66 Kelvin. So we get this as option C is correct. Next question. It states that a thermodynamic system is taken from original state D to an intermediate state E by a linear process as shown in figure. Its volume is reduced to the original volume from E to F by isobaric process. Calculate the total work done by the gas from D to E and E to F. So here basically it is a PV diagram. So the work done will be equal to area under the curve or area of the triangle. So we can say that total work done will be equal to area of triangle DEF, and which will be equal to half base into height, that is 5 minus 2 is our 3, and 600 minus 300 is our 300, and this goes by 150. So from here we get this will be equal to 450 joules. So work done is equal to 450 joules. So this completes all the 23 questions. So this was part 2 for the year 2022. So we have completed all the mains questions from the year 2022. Advanced questions are left. We will deal them later on. Okay, might be in next or next to next. So this completes all the 23 questions. Thank you.